Hey there, and welcome. Today, we're going to pull back the curtain on one of nature's coolest magic tricks. It's a trick that light itself performs every single day, all around you. It's called refraction, and trust me, by the end of this, you'll understand the secret behind the magic.
So we've all seen this, right? You take a perfectly straight straw, you pop it in a glass of water, and bam, it looks like it's broken right at the water's surface. What's going on there? Is it some kind of illusion? Well, yeah, it is, but it's not magic, it's pure physics, and we are about to break down exactly how it works.
All right, here's our game plan. First, we'll uncover the secret behind the trick. Then, we'll learn the rules that light has to follow. After that, we'll use those rules to explain some wild optical illusions, and even see what happens when light gets totally trapped. And finally, we'll wrap it all up with a quick recap and a little challenge for you.
Okay, let's get right into it. It's time to find out the why behind that weird bent pencil illusion.
So, the big secret? It all comes down to one word: refraction. That's it. Refraction is just the scientific name for the bending of light. It happens anytime light moves from one clear substance or medium into another one, like from the air into the water. So, the key thing to remember is, the pencil isn't bending at all. The light is.
But why does light bend? Well, it's because it actually changes its speed. Think about it like this. Imagine you're driving a car on a smooth paved road, and suddenly you hit a big patch of thick sand. What happens? You slow way down, right? Light does the exact same thing. Air is like that smooth road. We call it an optically rarer medium, where light travels super fast. But water, or glass, that's like the thick sand, an optically denser medium, where light is forced to slow down. And that change in speed is what causes the bend.
Now, this bending isn't just random. Light follows a very specific set of rules, a kind of code that scientists figured out a long time ago. So let's check out the 2 golden rules of refraction.
Okay, rule number 1. This is what happens when light slows down. When a ray of light goes from air into, say, a block of glass, it bends. But which way? It always bends towards an imaginary line that we call the normal. The normal is just a line we draw straight down at a 90-degree angle to the surface, right where the light hits. So just remember, when light slows down, it pulls in closer to that normal line.
So, what do you think happens when light does the opposite? When it goes from that slow, dense glass back into the speedy, rare air? Yep, you guessed it. It speeds up. And as it speeds up, it bends away from the normal. It's the perfect opposite. So the rule is simple. Slow down, bend towards, speed up, bend away. Easy, right?
Now, these simple observations are actually part of 2 official laws, sometimes called Snell's laws. The first law is pretty straightforward. It just says that the incoming light ray, the bent ray, and that normal line all stay neatly on the same flat surface. The second law is the math part. It's basically a formula that lets us predict the exact angle of the bend, which is amazing. It means refraction isn't random at all. It's totally predictable.
And how do we measure all that bending? We use something called the refractive index. You'll see it represented by the Greek letter mu. You can just think of it as a number that scores the bending power of a material. The higher the refractive index, the more the material slows light down, and the more it bends it.
And check this out. This table shows it perfectly. Air has a refractive index of pretty much 1, which means it barely bends light at all. Water is a little higher at 1.33. Glass is around 1.5. But then, look at diamond. Whoa, 2.41. That massive refractive index, that incredible bending power, is exactly why diamonds sparkle so much. They're like the world champions of light bending.
Okay, so we've got the rules down. Now let's have some fun and apply them to explain some really famous optical illusions. You ever look at a swimming pool and think, that doesn't look so deep, but then you jump in and it's way over your head? Well, that's refraction messing with you. The light coming from the bottom of the pool has to travel from dense water into rare air to get to your eyes. So what's the rule? It speeds up and bends away from the normal. But your brain assumes light always travels in straight lines, so it traces those bent rays back to a point that's much higher up, creating a virtual bottom. It's literally seeing an image of the bottom that isn't really there.
And this brings us right back to where we started. That bent stick, it's the exact same illusion. The light coming from the part of the stick that's underwater gets bent on its way out. Your brain sees a virtual image of that part of the stick, making it look raised up and closer to the surface. And that's why it looks like it's bent. Mystery officially solved. All right, so we've seen light bend,
But what if we could bend it so much that it actually gets trapped and can't escape at all? This leads us to the ultimate trick in light playbook, something called total internal reflection.
Now, for this to happen, two conditions are absolutely non-negotiable. First, light has to be going from a denser medium to a rare one, like from glass out to air. And second, the angle that the light hits the boundary with has to be greater than a very special angle, which we call the critical angle. Both of those have to be true, or it won't work.
Let's walk through this. Imagine a ray of light inside a block of glass. If it hits the surface at a small angle, it does what we expect. It escapes into the air and bends away from the normal. No surprises there.
But watch what happens as we increase that angle. The escaping light bends more and more, until we hit a very specific tipping point. This is the critical angle. And at this exact angle, the light doesn't really escape. It just skims perfectly along the surface, bent at exactly 90 degrees. It's right on the edge, about to be trapped.
And if we push that angle just one tiny bit more, so it's greater than the critical angle, boom, the light cannot get out. Refraction stops happening. Instead, the surface of the glass suddenly acts like a perfect mirror, and all of the light is reflected right back inside. That is total internal reflection. The light is officially trapped. How cool is that?
Whoa, okay, that was a lot I know. So let's do a super quick recap of the most important takeaways before we finish up with a final challenge to see what you've learned. All right, here's what you absolutely have to remember. Refraction is just the bending of light because it changes speed. It bends towards the normal when it slows down in a denser medium and away from the normal when it speeds up in a rarer one. This is what causes those weird illusions like shallow pools and bent sticks. And finally, when light in a dense medium hits the edge at an angle bigger than the critical angle, it gets trapped. That's total internal reflection.
And now for your final challenge. A few questions to get your brain working. First, what is the one thing about light that doesn't change when it refracts? Second, which color of light is the fastest? And third, can you think of two real-world examples of where we use that awesome total internal reflection trick? Ponder those, maybe do a little digging, and put your new knowledge to the test.